this is the chapter that has more number of equations. Angular speed, angular velocity is defined as angle by time. Angular speed, omega. And the unit is radians per second. That's theta over time, radians per second. But then you could relate angular speed to the linear speed with this formula. That's the relation between angular speed and linear speed. And that's the radius, of course. Then you have the definition for angular acceleration. And how would that be? Acceleration is always change in velocity by time. So here it would be delta theta. So that's a mistake. That's a mistake. I don't know why I wrote that. Don't write that. It's actually delta omega by delta t. I'm going to correct that later on when I realize. Please write that as delta omega by delta t. That's all right. Okay. But then again, A by R. That's the relation between angular acceleration and linear acceleration. Centripetal acceleration. Centripetal acceleration. Does anybody remember? V squared by R. We had that in circular motion. Or, yeah, what you were about to say, yes, omega squared R will also work. Yes.
With the little circle on either, is that velocity?
That's just velocity.
Okay,
Yeah.
sure you weren't...
Yeah, I just put that little thing to show it's a little, it's not a capital one. Okay, anyway. Torque. For you, torque has to be defined as R cross F. It is not just R times F. For you, remember, it's R cross F, and that is RF sine theta, which I have not written, but it is RF sine theta. And I'm sure you know how to take the cross product of I, J, K vectors, and this is only for university physics. I, J, K, you know how to take that, right? Cross product of R and F. We have done a problem or two on that. Angular momentum, I omega. But for you also have to remember, angular momentum is R cross P, isn't it? R cross P. Angular momentum, there are two formulas. Angular momentum is I omega, or it is R cross P. Where P is, what's P? The linear momentum, yeah. P is the linear momentum. So it's either I omega or R cross P. Then you know that I stands for rotational inertia, and it takes the place of mass in linear motion. And rotational inertia, specifically you have to know the rotational inertia of a rod, ml squared by 12. That is when the axis is through its center, yeah. But do you remember what the rotational inertia is if it's rotating about one end?
1/3.
Yeah, 1/3. It'll be ml squared by 3 for a rod.
12 or is that I2?
That's 12. Rotational inertia of a disk is mr squared by 2. mr squared by 2. And for a solid sphere, it is 2 by 5 mr squared. Okay, now I need to. Omega is 2 pi times frequency. Omega is 2 pi times frequency. And frequency is what is given in rotations per second. You know that, right? Rotations per second. So this is going to be in radians per second. Frequency is in rotations per second. And this is going to be in radians per second because one rotation is equal to 2 pi radians. That's why. And here I was just trying to show the college physics students, you know, that when you take the distance, you always have to take the perpendicular distance. You know that, don't you? When you try to calculate torque, you always take the perpendicular distance from the pivot. You take the perpendicular distance between the line of action of the force. Now, did you notice that I had changed this? So go back again and make sure you have written alpha this way. Okay. Something crazy happened to me and I wrote it that. Okay. Kinetic energy of rotation is 1/2 I omega squared. It compares to the translational kinetic energy as 1/2 mass times velocity squared. Oh, so wherever you have mass in linear motion, you're going to have rotational inertia in rotational motion. That's what I'm trying to show.
So what's the KR for the first one?
Rotational kinetic energy, and KT is translational kinetic energy. That means energy in linear motion.
Translational?
Yeah. Translational kinetic energy. I don't know. And then, don't worry about that. All right, the other equations compare with kinematic equations. You know that VF is V naught plus AT compares to omega F. It's omega naught plus alpha T. VF squared is equal to V naught squared plus 2A delta X compares with omega F squared is omega naught squared plus 2 alpha delta theta. And the king of all equations, delta X is V naught T plus 1/2 AT squared compares with delta theta is equal to omega naught T plus 1/2 alpha T squared. There is another very useful equation which usually people don't write, but this one is useful. It doesn't have acceleration in it. It's just average angular velocity multiplied by time gives theta. Finding them how to change degrees into radians. And I just gave an example. 30 degrees is pi by 6 radians. All you got to do is multiply with pi by 180. Okay? So if you want to change degrees into radians, just multiply the degree with pi by 180. Because pi radians is 180 degrees. That's all I was trying to show them.
So it would be 180 over pi for the other way around?
Yes. Trying to tell them how to calculate the velocity of, I think it's a sphere that we consider rolling down an inclined plane. You remember that? Mm-hmm. Yeah, I'll just go through it fast. At the top, it has potential energy. And as it rolls down, it has both rotational kinetic energy and linear kinetic energy. Now, that step is the same for any kind of object, you see? But from there, it'll change. You know why it's going to change? Because yeah, the I is going to change. If it's a sphere, then it becomes mr 2 by 5 mr squared. And you do know that omega is V by R. So, and we've done this. And then you can cancel some of those terms. And 1 by 5 plus 1 by 2 is 7 by 10. I know we've done exactly the same thing in class. So, and that will let you find the velocity. In that, I just gave the height as I think it was 5 meters or something, and that's how I got a number, okay? Don't worry about that. It's trying to do some problem with them. Momentum is the product of mass and velocity, right? And then you have conservation of momentum, where the total momentum before collision is equal to the total momentum after collision. That is the principle of conservation of momentum. So you have two objects. Their masses are m1 and m2. Their initial velocities are v1 and v2. And their final velocities are v1 prime and v2 prime. Is this true for both elastic and inelastic collisions? Did I hear a no?
No.
Momentum is always conserved. Whether it's elastic or inelastic, momentum is always conserved. So yes, it is true. Now, what is not true is kinetic energy is not conserved in the case of an inelastic collision, right? Remember that. So that's a big difference. So momentum is always conserved for both elastic and inelastic. And then I tried to give an example there. And I said, what happens if they stick together after collision? And I was also trying to, you see this negative here? That's if the problem says the second object is coming in the opposite direction. See that? And many students forget that. Please make note of that. If the second object is moving in the opposite direction, you will have to take its speed as negative. Rather, its velocity as negative to be perfect. And if they stick together after collision, then that is a perfectly inelastic collision. That is where you have maximum loss of Ke, maximum loss of kinetic energy. And if you imagine that they stick together, you've got to add their masses, isn't it? And final velocity can be found out. It's just that. Then you have impulse. What are the two equations for impulse? One is force multiplied by time, and the other is change in momentum. So you have two equations for impulse. Force multiplied by time and change in momentum. You remember? Ballistic pendulum. You had that pendulum hanging down there, and you shot a ball into it, and you were trying to find the...
Angle.
No, actually you were trying to find the velocity with which the ball was shot out. Yeah, first you measured the angle. From the angle you calculated the height. From the height you applied the conservation of energy and found out the velocity with which both of them begin moving. Then you applied the conservation of momentum and found out the velocity with which it was shot out. So there are three steps there. Again, number one, from the angle. How did you find the height from the angle? And you know, this came from a college physics student who straight away gave that equation. I was so happy. That's what we use for the lab. H is equal to L minus L cos theta. What is L there? L is the length of the pendulum. Length of the pendulum. And then from there, you go ahead, you apply the conservation of energy and find. And when this was written down, I just want to ask you this. How many people understand? What is this velocity here?
And when it's in motion?
When it begins its motion. And at that point, actually the projectile is stuck in it, isn't it? That's why you have the masses added up. If that's the case, then this is wrong on the left side. Because the masses should be added up. I don't know. It depends. A review is not just giving me the exam questions. You have to be really listening. So I went ahead and changed that because I was just playing with them, saying what is it, and, you know. And then I put V final so you're not confused. That's the velocity with which both of them begin their motion upwards. Is that clear?
Yeah.
So the kinetic energy that they had there becomes equal to their potential energy at the top. Now, from that equation, can you find Vf? Yeah, because you just now got H. You can find Vf. And then you have to apply conservation of momentum. Why is it a big zero here? Because initially the pendulum was not moving, okay? And then that's how you get the velocity with which the bullet or the projectile was shot out. So since it's a lab, everybody's supposed to know exactly what you did, so I can twist it a little bit and you should be able to do that. All right. I give you the mass of the meter stick. I can't remember what I said, but let's say it's 115 grams. I think that's what I said. 115 grams. And I give you the center of mass at 52 centimeters. So 115, you want to write this down. 115 grams is the mass of the meter stick. 52 centimeters is its center of mass. And I give you a 100-gram mass, another 100-gram mass, and an unknown mass. So 100 gram and an unknown mass. Everybody should be able to set up a diagram to show me what you would do to find the unknown mass. So go ahead, take 1 minute to do that. Draw a diagram to show how you would find the unknown mass.
Value, like the unknown mass?
If you have the pivot at 52, exactly at 52, would you have to consider the weight of the meter stick when you calculate?
Not necessarily.
Not at all. So that is exactly what you should do. It's up to you. So when I give you the mass of the meter stick, it doesn't mean that you have to use it. That's a good question that he asked. That's exactly what I was trying to drive you to. So you would set up something like this. Okay, it was 115, 52, and the 100 gram, and unknown. You would try to set it up. If that's the 52 centimeters, you would put the pivot exactly there. 100 gram on one side, let's say at 75, and the unknown mass at 25. Remember, I've not given you the numbers. So, yeah, you can cook up any number you like, but your answers are going to be different, and I don't care, you see. I mean, as long as you know what to do. So, that type of a question maybe you've never seen in your life, but you got to. The idea is, can you find the unknown mass? That's it. Yes?
Oh, so it doesn't matter where in the meter stick you put the 10?
It doesn't matter. Your answer is going to depend on your picture. What do I care? Because it's like each one got a different unknown mass, and each one is just using their thinking to put it where they like, So expect questions like this. I'm not saying just this one. Questions like this. Because that gives me an idea of, oh, you really know what you're doing. Okay. So in this case, m times 52 minus 25 is equal to 100 times 75 minus 52. Isn't it? Which would give you 85.2 grams if you had my exact numbers.
Yeah, I did it on the end and I got 1,061.
Yeah. You got what?
1,061 grams on the very ends.
Okay. That's fine. But did it go up to that big a value?
I think it's supposed to be 100.
Because it went up to what? 1,061. That
Do it on the end.
another meter stick, and that meter stick has a mass of 125 gram. Write it down, please. 125 gram. Its center of mass is also at 52. And I give you 100 gram. Like before, I give you 100 gram. And I want you to find the mass of the meter stick. Okay, scratch out the mass of the meter stick. Sorry, I'm not giving you the mass of the meter stick.
See, I caught that. I get extra credit.
You have to find the mass of the meter stick. The only thing you have is, you have a meter stick, its center of mass is at 52, and I've given you 100 gram. Use this, draw a picture to show me how you would set it up so you can calculate the mass of the meter stick. This is what we did in the lab, remember? Go ahead. I'll give you 1 minute.
I mean, it's going to be way more on the other side, obviously, but I don't know.
Okay, this is the question. You'll have to set it up. That's the center of mass. That is the mass of the meter stick. You put the 100 gram on the other side. And the pivot, I just assume that it's at 40, right? Can you balance this? Yes. Because this is the clockwise torque, which would be m times 12. M times 12 is equal to 100 times 15. Problem done.
So you could just make up any value in the fulcrum?
I mean, as an engineer, what are you going to do? As an engineer, your idea is, hey, you find the mass of this meter stick. You're given 100 gram. Nobody's going to tell you, it's at 10, this is at 15. Nobody's going to tell you. Just use what's given. That's why I had that 125 gram in my head, Because when you calculate, you get 125 gram. Yeah, and I wrote all this while I was teaching them. I did not intend to record it, and then I thought, yes, let's...
This one just like the last one where it could be any number?
Yes, any number. Static equilibrium, you have problems with two supports Haven't we done that? Problems with two supports. What are the two conditions for equilibrium?
Net force is equal to 0, net torque is equal to 0.
There you go. The total up force is equal to the total down force, and then the total torque must be
0.
okay. So just to show that, with the same meter stick, you can see that that's the same meter stick. It's supported at 2 points, and one side you have a 50 gram at 10, and you have 100 gram at 72. And this is at 80, this is at 25. And the two supports, the reactions at the two supports are N1 and N2. Can you find out N1 and N2? That's the question.
So you take both distances from 25 and 10, or do you add those into?
No, you have to use both the conditions. What's the first condition?
No, net force is equal to 0.
N1 plus N2 must be equal to the sum of the other three, which is 275, I think, isn't it? 125 plus 100 plus 50.
All the normal forces are equal to the.
The total up force must be equal to the total down force. Yeah, that's the first condition. Because if it's not so, it will move. Now, since it's neither moving up nor down, it should be balanced. So translatory motion is cancelled. You see that linear motion doesn't exist. Now, the second thing, you will have to calculate the torque at one of the supports. At one of the supports, any one. But I always like to have it on the left side because it's easier to show. So I'm going to calculate the torque here on this support. Okay, tell me this. What's the torque due to this here? N1.
0 because
Zero.
down and up.
Yeah, it's not there. So you have two clockwise and you have one counterclockwise. Actually, you have two counterclockwise. Did anybody see the second counterclockwise?
Yeah.
This is counterclockwise, isn't it? And this is also counterclockwise. So, and then there are two clockwise, that's all. So 125 times that distance, which is 27, plus 100 times 47 should be equal to 50 times 15 plus N2 times 55, from which you can calculate N2. I did not finish it because that's just simple math. Find N2 from there and then plug it back into equation 1. You get both N1 and
Where's
N2.
27 and 47 come from?
The distance?
52 minus 25.
52 minus 25?
minus-
Because now all distances are going to be measured from here. Because you have assumed that to be your pivot. So 52 minus 25 and 72 minus 25, that is 47, and 25 minus 10, you see. Makes sense, doesn't it? Modulus, Young's modulus. Do you know the formula?
Yes.
Then if I give you that the percentage of extension is like 3%. Okay? What does that mean? And then I'll give you Young's modulus and I want you to find the force.
Isn't it 3% delta L?
3% will be delta
Oh, L
over
over delta L.
So it'll be, yeah, but will that be 3% or will that be 0.03?
It'd be
So
0.03 over
03 in the
100.
No,
problem.
it'll be 3 over 100,
0.03.
which will be 0.03, okay? I think I've written this down. And again, A would be pi r squared, isn't it?
Yep.
Where r is the radius. And then if I, GPA, you know what GPA is? Giga is 10 to the power 9. So you have to know that. You know, little things and you miss out. And then I think, okay, I gave the area directly as 0.003, all right, without giving the radius. And I was asking them to calculate the force. Oh, maybe
You said the 3% was.
I did not write after that. Yeah, the 3%, let me write now. The 3% is change in length over the original length is 3 by 100. So that's 0.03.
You're giving us the area, right?
Yeah, I've given you the area. And then when you plug it back in here, you have to be careful. Are you going to plug it in as 0.03?
No.
I've seen several students do that.
Plug it in as 3, right? Because it's the other
What are you going to plug it in as?
100 divided by 3, 33.3.
Correct. Or 1 divided by 0.03.
So, why don't you
I've
give
seen
it to us?
several students do that. Several. They will just take that. They won't even care, to look at the formula, and then 5 points gone. Well, surely that's not good enough for an engineer. You know what I mean? Say, you got 0.03. Reversed, you put it. So be careful on such things, and your grades will go up. One of the things that I like, fluids. This is our next chapter, the last chapter.
So why don't you put in this 0.03?
Because it was 1 by 0.03 in the formula. I'll explain that later, personally. Pressure exerted by a liquid, H rho G. H is the height, rho is the density. Okay. But fundamentally, pressure is force by area, isn't it? Force by area. Unit is Pascal. Archimedes' principle is very good, and I just gave them a question which you have. Go to question number 9 on that and do it. On the problem set, go to question number 9 and do it. That's a good question just to see whether you can do. If you did not pick up the problem set, it's there. The review is on the table.
The P equals, what does that P mean?
That's pressure.
Pressure? And the P inside is
That's not a P.
Rho.
That's a hunchback.
Rho is
That's a
density.
rho, density.
Okay.
So everybody try to do number 9 in the next 3 minutes, because if I keep talking and you don't do anything, you're going to sleep soon. Is how much is above water. What we are interested in is how much is below water. See that? So I had to play a small trick there. Aren't we interested in what volume of the fluid is displaced?
Yes, you take the 3/5 7,000, correct?
So that'll be 3/5 of 1,000, which is 600. And now I just wanted to give that as a formula. Buoyant force. Buoyant force or the upthrust is equal to, can anybody help me out on that? Buoyant force is equal to what?
So the water displaced, isn't it?
It's the weight of water displaced. And the weight of water displaced would be its volume times density times G. Okay, I'm talking about this. Everybody needs to know. Buoyant force is volume of the fluid displaced times the density of the fluid times G. All right? And if the problem says something is floating, then don't you know that its weight is exactly equal to the buoyant force? Isn't that why it's floating there? So I'm trying to set that up. I'm saying, yes, the weight of the object is equal to the buoyant force. Isn't weight equal to mg?
Yes.
But isn't mass volume times density? Yes. So now you have volume of the wood times density of wood times G. That's the weight of the solid is equal to weight of the fluid. Cancel the G's. And I did this problem for another number. I did it for 3 by 5. Okay, so the answers will not be the same. You know what I mean? Here I was telling them that 3/5 was above water. But in this problem,
2/5 is below.
2/5 is above water, 3/5 is below. So for me, it will be the other way around. 3/5 above, 2/5 below. Okay.
So the buoyant force of the solid is equal to the
Buoyant force of the liquid is equal to the weight of the solid. In this problem, it's only 2/5 that was underwater. Therefore, it's having a lower density. Isn't that clear? Okay, 400. Easy. And then I'm sure we did a problem on, did we do it here, a mattress and how many people can stand? Yeah, so with that, everything's clear there. And also we did a helium balloon problem, didn't we? Yeah, yeah. Clear. Take note of that. Floating, weight of the floating object is equal to the weight of fluid displaced. With that. And then we come to Bernoulli's principle. And along with Bernoulli's principle, you need to have the equation of continuity. This is the last part that we did, so I think I told them about that at the end. Bernoulli's principle. And usually it's applied to a horizontal pipe. You know, if it's a horizontal pipe with different area of cross sections, A1, or caps A and small a, and the flow velocities are, you know, different, caps V and little v there. Do you know what the equation of continuity is? Yeah, A1 V1 is equal to A2 V2. Or, because I've used different symbols. And then Bernoulli's principle is rho V1 squared, yeah? Rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Agreed? Well, then I try to do a problem with them, which you need not, because I've already given you a problem. Let's go to number 10 and try to do that. Number 10. And do that, but please change the last sentence where you see 10 centimeters of mercury. Please make it 50 centimeters of mercury. Now, the reason why I wanted you to do this, now this is going to write on top of that. Okay. The reason why I wanted you to do this is because, and you see, I'll fly through this. You either listen to me or you talk. You can't do both. Frequency is 20 rotations per second. Some people take this as omega, which is wrong. Yeah, many people take that as omega. I don't know why. Rotations per second is not omega. Rotations per second is frequency. That's not omega. To get omega, you got to multiply frequency with 2 pi.
Radians per second.
Then you get it as radians per second. Once you get that, you use this formula and find the linear speed. You will get it as 20 meters per second. Done. This was this a multiple choice? Yeah. Multiple choice question with radius given. Here it is 1 meter, okay? I told you to take it as what? Centimeter. Don't worry about it. So the answers will not agree, but here it's 1 meter. So if it's 1 meter, then who cares about the answer? You just care about how you do it. I tried to derive the formula for centripetal acceleration, but finally it comes to omega squared times r, and so.
So you want to convert the centimeters to meters?
Oh yes.
It was the other way around where.
Because radians per second will only go with meter per second. What did you get the answer as? Of course, you got less. But yeah, that's fine. Number 2 done. Number 3. The king, yeah, there you go. The king is the equation. So alpha is given, 4.5 radians per second squared. Omega naught is 1 radian per second. You can see the difference in the units. Time is given as 2 seconds. Use this equation. And get it. $11 radians. See, I just want to add something to this question to make it kind of your standard. Not much. But if I had asked you how many times did it rotate, would you be able to find out? Divide that by 2 pi, that's it. Because each rotation is 2 pi radians, isn't it? Mm-hmm. That's it. So at your standard would be a little bit more maybe. Yeah, 11 divided by 2 pi, whatever you can. All right, number 4 has something in it. Number 4 is getting better. Number 4.
Yes. Frequency, yes.
Did you notice in number 4 that you're asked to find the angular acceleration, but you're given all linear terms?
Yes.
So can't you first find the linear acceleration? and then convert it to angular acceleration. You find A, and because you know alpha is A by the radius, you get it. So radius is 34 centimeters, 0.34 meter, V naught is 8.4, final velocity is 0, delta x is 115 meters. And I'm already giving you the final relation. Alpha is A by R, so find A using your kinematics equation. And because it's slowing down, it's actually a deceleration, isn't it? Yeah. So that's what you get for number 4.
It's asking for the angular acceleration of the wheel.
I am not going to give you the answer. Okay, you don't have the mass. Let me just echo what you're saying. You don't have the mass. Do you know at what point the mass is acting through? Thank you. Now, so you know that the mass, just assume it to be m kilograms, is acting through the center, right? And so now the torque is going to be that times half of the, which is 2 meters, right? Write that down. You got an idea. Torque is mg, because mass is not given, it's mg times 2. Everybody understood that? Mg multiplied by 2. Why? Because it's the weight is at the center. And that's 2 meters away from the hinge. Okay, what's the other formula for torque?
R cross F?
R cross F we already used. I alpha. Torque is I alpha. So,
Did you give us that today?
not today maybe. Add it. No? Put them equal to each other.
And you figure out alpha.
I omega is angular momentum. Torque is I alpha.
I alpha.
We have like 2 unknowns though.
Don't worry. Just put those two together.
So I alpha equals mg times 2.
Yes?
2 divided by 12.
And then I is our, for a rod ml squared.
Hold on. Good point. He's bringing up I for a rod. At what point is it rotating? At the end. What's the I? Right, thank you. I is ml squared by 3. Plug in that.
So the m's cancel.
Is it safe to keep the mass can be pulled?
What?
Mass is
Or you can agree.
Mass is what?
1.
Oh, you can assume any mass.
So where do we get 12
Yes,
from?
because it will cancel out. Who cares? It cancel out. Whether you use 1 or 10,
And the other one's 112.
doesn't matter. Okay, here is the problem.
Which L do we use?
All right. That's the problem there. I is ml squared by 3. I get the I first. Torque is R times F, which I already told you, 2 times mg, 19.6 m. And torque is I alpha. Therefore, alpha is tau by I. But I know that tau is 19.6 m and I is 5.33. Cancelled out. 3.68 radians per second squared. This is what I call a good question. No, we're just getting to that. We're just getting to that. Okay, this is how you do number 6. That's the disk, the mass hanging down there, causes a force which is 1.53 times 9.8. Yeah, because you're actually looking for force there. So that's 15, and then torque is radius times the force. And then, do you know where I got the mr squared by 2 from? Sure. That's for the disk. The rotational inertia of a disk.
So you need
Mr squared by 2.
you need to change the. Okay, yeah, I see.
From Google. What are you saying? Okay. No, he was saying something from, get it from Google or something. Oh, you said I got it from Google. Okay. Come on. So that is the rotational inertia of the disk, 1.54 kilogram meter squared. What are we looking for? Alpha. So now you know how to finish it, just like we did before, right? Yeah. You know, but this is something that people forget. Look at what I did now. Look at what I did. I found the rotational inertia of that mass.
How'd you do that? The disk? First you did the disk?
Yeah, I found that of the disk. Isn't this also moving?
Yes.
Isn't it also moving about an axis here? Because, see, the distance is constant, isn't it? The mass? I'm not talking about this distance. I'm talking about the line of action of the force, which is where through the mass. So it has the rotational inertia.
You're adding that to the other.
Yes. So to get the total rotational inertia, you need to add both of those. Get the total rotational inertia. When I add it, that's when I got 2.20. That makes this a good question, because you would have forgotten about that. You see, you would not have considered that. So now that becomes a good one. So .5 radian per second squared. Here it goes. Number 7, we've done it. No. That's not the one that we did. See, your number 7 does not agree with that. That's why. The number 7 that you have, we have already done. Nobody remembers? MGH is equal. Okay. So now you have a fresh problem. You can write that down and try to do it. I mean, why not? Just write that problem. Yeah.
I don't remember, man. I was doing the other one.
Yeah, 7 we have done, 8 we have done, 9 we have done, 10 we have done. Does anybody understand what I did just now? Go back and look at 7, 8, 9, 10. We already did it. Look. So I started with 7, 8, 9, 10 and finished this. So this is done.
Right now, my life is jumbled. Can't even remember what I did yesterday.
Okay.
We're going,
So
we're
try
in
to
the,
take that and try to do it.
we're in the cleaning.
I think my
Professor's
memory
house.
capacity is terrible.
You know, do you know that memory diminishes with age?
Really?
Yes.
But do you know that those who stay in the field of education, their memory doesn't diminish?
Well, that's why I tell you to read, because
Yeah, it doesn't.
Jump your brain.
It's amazing. My memory is falling, but it's falling at a much slower pace than other people. You know, my friends. You know what I mean. Who are not in the field of education, they're not reading anything.
So we're like
They are not thinking.
friends or
Well,
what?
yeah, you go to work and it's,
Yeah. So if you're doing physical labor, your memory is
You don't
No.
think it's hereditary?
I don't know. I find it.
Yeah.
I think a lot
Little,
whenever
yeah.
I
little
work.
I think
Yeah.
it is.
little bit. Don't try to blame everything on dad and mom, okay? It's only a little bit. We can change it all. Off.
starter hits the flower and then it turns the.
Oh, you want a moment of inertia? What is it? What is it? Yeah, it's I, but what is it?
Flywheels?
The disc.
Disk. What's the formula for moment of inertia with disk? mr squared over 2.
It sucks changing.
Yeah. mr squared over 2.
Well, what is the energy part of it?
That is required.
Rotational kinetic energy.
That's what that is.
Uh-huh. What's the formula for rotational kinetic energy?
1/2 omega.
1/2 I omega squared. So, come on now, what is that? That's terrible. I mean, it's just plugging in those two numbers, isn't it? Why do we waste time on that? Okay, do one thing. I think those problems are not standard, because that's for college physics. Pass this out. Let's do this. Those are, I mean, just substitution type. Unless I find a good one, I'm not going to make you do that.